So hi everybody. Today we have the pleasure of introducing Sebastien Desigual, who's going to, well, he was a former student of Nicolas Brunet, right? And for the last half a year, he's been working in the Institute of Optimization Theory, I understand. He's going to speak about the fusion or the synergy between optimization theory and locality. Okay, Sebastien?
Thanks. Hello, everybody here and also online. Thanks for having me here. And I'll indeed be telling you about this recent project that I've been conducted in Berlin at this Zuse Institute since last autumn. The project is now online for like 2 weeks. And the goal is to use developments in optimization for non-local problems, and namely to construct local models and Bell inequalities. And the main, let's say, advantage that I had going for this interface with this community is that they have, let's say, refined a technique that was rediscovered by Miguel and others, but I think you were the main rediscoverer, let's say, a few years ago, and known in the quantum community as a Gilbert algorithm. These Frank-Wolfe techniques are basically, let's say, another rephrasing of this that allows to use the techniques that they've developed recently. The paper focuses on two main applications, although it's completely general. The first one is going to be the non-locality threshold of 2-qubit Werner states, which is a long-standing problem on which Flavien and Miguel have worked in the past. And the second application will be tripartite states, for which lower bounds on the non-locality threshold were basically really rough, and we almost doubled them, actually. The entire talk will be around this diagram that summarizes the method that we've used. So I will slowly guide you through the different parts of this methodology. Let me just quickly show you what's happening. So we are choosing at the beginning a quantum state, and we are interested, this is the main goal, in the non-locality threshold of this quantum state. And at the end of all this procedure, we end up with an upper bound on this non-locality threshold, and a lower bound. First, I will tell you about the quantum part of the talk, then we will forget about that. It will just be polytopes and an algorithm dealing with this. And at the very end, when telling you about the results, I will go back to the quantum realm. But let's start by defining what I mean by those correlation matrices and stuff. We are dealing with a scenario that I guess is familiar to most of you, so I will not expand that much on this part, but okay, if I'm too fast, just stop me. I want it to be kind of interactive, except for you online, I'm sorry. And although I represent it here as a bipartite scenario, it's general for multipartite scenarios. By repeating this many times, so Alice and Bob getting questions X and Y and outputting answers A and B, you construct this probability, and depending on the strategy you're actually implementing, you can get different, you have different, let's say, probabilities available in this space of probabilities. If you're restricted to like classical correlations and let's say a local hidden variable lambda and the local strategies on both Alice and Bob's side, then this is the shape that probability takes. And with quantum mechanics, if you allow for a quantum shared state and measurements on Alice and Bob's side, you can get something of this shape, and it is known since Bell's theorem that this can actually outperform this. Namely, you can get a probability distribution of this shape that cannot be written like this. In this talk, I will mostly tell you about the case where the number of outputs is actually 2, because in this case we have like a nice correlation notation which will turn useful in the following. And then in this case, we don't talk here about measurements, but about observables having plus or minus eigenvalues. I will also denote all the correlation tensors appearing with this bold symbol. In the case of a qubit shared state, these observables, they take a simple form with the Bloch vector AX being in the Bloch sphere. So far, so good, I hope. Now, if I fix the number of inputs in my scenario that I will call M throughout this talk, then what's accessible classically is a polytope. A polytope in dimension M squared and whose no marginals at the moment, but the methods work for marginals as well. And whose vertices are actually given by those deterministic strategies, and there are actually a lot of them, because you can choose basically a plus or minus sign for each of the two M, A and B, and this amounts to a lot of vertices. I will just give you an example so that it's clear, but probably you know about it already. If I restrict to 2 inputs, so M is equal to 2, then these are typically the deterministic strategies, right? You can see that they indeed factorize. Like this one is, for example, minus minus times plus plus, and so on and so forth. In this simple example, Bell, CHSH, gave a quantum strategy that is not reproducible by classical means. And this strategy uses those of the observables and the singlet state as the shared state, or you can use the singlet state to violate CHSH. And you end up with a correlation matrix of this shape. And you see here that it's not any of those vertices. So it's a point that actually is not in the local polytope. But if you kind of divide it by the square root of 2, so making it closer to the center of your space, then you can actually find a decomposition. And this here indeed reproduces this point. And all those points here, the 4 of them, they're actually local vertices, like deterministic strategies. Now that I've introduced all of that, let me tell you a bit more formally what we are interested in. What we're looking for is to bound the non-locality threshold given a quantum state. And this non-locality threshold is given by that. Like this is the infimum of this set. So you're looking for a number of inputs and observables such that when mixing, when being on the line between your point P and the origin, you actually are not in the local polytope. And when computing this, you end up with this non-locality threshold. Is it clear so far? I guess you're kind of familiar with that, so OK, perfect. I will also mostly work with projective measurements in this talk, but OK, probably at the end I will tell you about ideas for more.
Just check if this quantity is greater than or equal to 1 if it's a local quantum state that you chose in the first place, right?
Sorry, say it again?
If you go back one slide, so this formula, like, it will take a value greater than 1 if your variable that you started with is local. Yeah, exactly.
OK, so now I've told you about this quantum part, and now we move on to the center of the method, which is this algorithm. As I mentioned already, this algorithm, at least the original version, was known in the quantum community, but I will slowly guide you through what it is on the one hand, and also what improvements were brought to it by optimizers, let's say. So the original algorithm works as follows. You are in a polytope. You start on a point x0, and you want actually to go to this point x star. In general, Frank-Wolfe algorithms work with any convex objective function. But in our case, we are interested in the objective function being the distance. So what we want to do is to minimize the distance between this polytope and this x star. So in this case, it's trivial. The answer is 0, and you want to basically converge to this point. With the distance, what's nice is that the gradient is actually just the arrow joining x0 and x star. So when I say I want to optimize the gradient over the different vertices, I will basically look for the vertex which has the strongest overlap with this gradient. And this is exactly what this original algorithm is doing. So you start with a point x0, and you're going to shoot in the direction of the best vertex. So in this case, the gradient is like that, so the best direction is this one, and you stop when you're closest on this line to your point of interest. And you can do that once. And the second time, in this case, the gradient was like that, so that the best point, the best vertex, was this one. And you again stop on the best point on this line. And in the original version, that's it. That's what you're doing. You're actually doing that repeatedly, like repeatedly. And you end up with a few iterations, many of them actually. You end up to the x star, to your objective point. This behavior here that you can see, this zigzagging, is what makes this original algorithm a bit like limited, let's say. And this is mostly this behavior that we want to avoid in order to get better. And the way to do that is to store the vertices you're using to decompose your current iterate, and to use this storage information in a good way. So in this picture now, I'm telling you at each iteration what I do have in my active set, so my storage set, to decompose the current point, the current iterate in red. So this is, at the beginning, just x0, so only x0 is red. But if I shoot a first time in the direction of the best vertex, exactly as before, now I have 2 points in this active set, right? And my x1 I can explicitly write down as a convex combination of those 2 points. And if I repeat, I end up with a third one. And now, geometrically, you can see that basically you have everything you need. You just have to kind of, handle a bit the weights in this active set, and you will end up here. And this is what this technique is doing. It's allowing you to, on top of sometimes going for the best vertex, but it's allowing you to move along lines inside your active set. So in this case, it would be here, okay, given this gradient, the best atom, the best vertex that I do have is this one in my active set. And the worst one is this one. So I typically want to place some weight from this vertex to this one in order to kind of reduce the weight that this one has because it's so bad, let's say. And the way you do it, geometrically, is basically to move on this line, which is parallel to this one. And you stop, as usually, when you have reached the point closest to your objective. And if you do this a second time, now, with this gradient, the best point is this one, and the worst one is, again, this one. And then you move, again, on the line parallel to this one, but going through your iterate. So you're moving, again, some weight from this vertex, which is not so favorable, to this one, which is better. And by doing so, in this example, actually, we end up dropping this x0, because otherwise we would go out of the polytope, right? This you can see in the decomposition that you're updating in the algorithm, because the weight typically goes to 0. And then you drop this x0, and you are left with this line here, which is exactly what you want. In sense that if you go for a last iteration, like mixing those two, which are the last two vertices in your active set, you recover precisely the optimum x star.
Sebastian, I completely lost it.
Oh, sorry.
Because you don't put formulas, and for me it's a bit difficult to know what it is that you're doing. So you start, okay, so this is the first step, right? I mean, this is the way it was before. Okay, this is the first step.
Yes.
Yeah, so then continue. Okay, this is the second step, this is as before, as you explained before. Now the new thing, the parallel lines, is the part I don't understand.
So this parallel line, so what I'm doing, I can write down formally what I'm doing. So I have typically, I have a weight, let's say P1 on, or I will go for 0, P0 on X0 plus P1 on X1 plus P2 on X2. And this is my, this is my current iterate. Sorry, I will name them. Yeah, exactly. I should name them some. Let me name them alpha, beta, and P2 gamma. These are my triangle, right? Alpha on top, beta the second one, gamma the third one here. And what I'm doing in this step is that I'm lowering alpha and placing the weight from here to beta. So I'm moving along the... Exactly. So what you're doing is typically saying, okay, I want to typically go for P0 minus P alpha plus P1, sorry, plus P beta plus P2 gamma. So I'm moving on the line between alpha and beta.
Okay, sorry, and the direction that you use to decide that beta is the best one and alpha is what is the direction?
So the direction is given by the, so you have your...
Okay, this is the gradient with
exactly.
the last point with respect to the point you want to...
Exactly. So you have this gradient here, and there is a best point in your active set. This is this one. And there is a worst point, and this is this one. Is it also confusing?
Why is the best point? I mean, you're going from X3 to...
No, from X2. Now I'm
from X2, okay.
from X2. In this direction, X2, I'm going slightly to the left, and then this is the best. And for the next one, you're right. For the next one, slightly to the right, this is going to be the best one, and this is still going to be the worst one.
Okay.
Yes?
So the active set will just increase whenever you would go in a new direction, or do you limit the size of the active set?
When I'm doing that, I'm just shuffling the weights in the active set. So I'm not increasing its size. But when I'm shooting in one direction with that, I'm indeed increasing its size by 1.
Is this an example, or you always have 3 points?
It's just an example. So in my actual implementation, we have a dimension that goes pretty high. Let's say hundreds of thousands of dimensions.
But you always have the worst and the best.
Yeah, exactly. In your active set, yeah. This you can do. I mean, it's not too big, so you can do at each step to find the best.
The worst gets dropped out, so you always kind of...
Not necessarily. You see, in this example, the worst is not dropped out. It's still here. But in the next step, what's happening is that when you're doing that, you see that in order to get closest to X star, you would need to have a negative weight actually on X0, because the optimal would be like a bit outside the polytope. And this you see because the corresponding weight here is going to get negative. No, bigger than... You see it.
Yeah, when you make it negative, you know that your point is still inside the point.
Yeah, exactly.
So you make it 0.
Yeah, you make it 0 and you drop the X0 then. Yes?
But sorry,
No, it's very important. This is the main...
So you shoot or you do this parallel thing, but this can go, so once you have an active set, it can be that there comes a new vertex that you have to add later, or you
Yes.
first find an active set and then you just work with that.
So at each step, so the question is, for online, I guess, the question is...
Sorry, I forgot. When you make a question, please use the there's a mistake. Maybe you could repeat the question, or I don't know.
Okay, so I guess what I was trying to understand is that if there is a next step of the iteration, do you first check that there is no new vertex to add to your active set before you do this parallel shifting, or is there somehow a step where you find an active set and then you work just with that?
So those steps, they're always done, let's say, you have a way to decide which step is more favorable for you. And at the beginning of the algorithm, especially in high dimensions, the best you can do is always to find a new vertex and to add it to your active set, right? And progressively, the balance would be more in the direction of doing those pairwise steps. And then you're doing them most of the time. The way you're actually choosing between those two steps is by estimating the gradient. So you have a way to estimate your local gradient at your current iterate. And if you see that you can do more progress with this step, then you will not you will even not compute the best vertex, because it can be costly actually. So this is one of the like subtle part that they understood like recently in this Frank-Wolfe community, how to accurately estimate this trade-off, let's say, between the pairwise steps and the kind of discovering steps.
Do you also use characteristic theorem to reduce the active set, or?
Not in this version that we're using. So they have versions that are still quite experimental that do that, but we're not doing that in this project. Okay. Other questions? So this was a really important part because this is the central algorithm that you're using. So don't hesitate to ask other questions if it's not clear. I will go one last time through this just to make it clear. So in the first step, we have only this in the active set, because...
so the online people say that if they don't see the laser pointer, can you use, when you at least highlight the points
yeah.
for this part, use the...
It's a fire extinguisher you can use.
I will...
No, but the slides are shared, so they see the computer screen.
Okay. Yes, so I can do that, and then they're seeing. So this here is the first point. It's in red because it's in the active set. So initially, your current iterate of the algorithm is here, and its weight is 1. The first thing you're doing is you're going in the direction of the most favorable vertex, which in this case, because the gradient is like that, is this one. And you stop on this line here because it's closest to your objective point. Then you add in red this vertex to the active set, and you remember the weights of this point, which I called alpha on the blackboard, and this one, which was beta, to basically reproduce your current iterate, x1, which is now on this line. And if you keep going, on the second step, you add another vertex, which is this one here, which I call gamma. And you're also doing, now you have a representation of x2 as a convex combination of alpha, beta, and gamma. And in this very simple example, this is all the vertices you need to kind of reach the optimal. So once you have this, you can only move along lines that connect two vertices of the active set. And this is done in this step by taking off some weight from alpha, this point here, and putting this weight in beta over there. And again, you decide where to stop on this line using the fact that you want to get closest to x star. And if you do this once again, now the closest point is outside the polytope. So when you're moving weight out of this point to this one, you end up, you would end up with a negative weight on this point here to get closest to x star. But since you want a convex decomposition, you say, oh, I will just drop this point because it's so unfavorable that I would need to go outside of the polytope to use it. And you end up with an active set that only has two vertices. And then the last step is going to get exactly to x star. So at each step of the algorithm, you have an explicit decomposition of your iterate in terms of points that you know, because you have found them beforehand by means of this best vertex that I'm going to tell you now about. Is it clear now? So the geometrical intuition from this is actually pretty reliable because it works as well in higher dimensions. What is slightly more complex in higher dimensions is that you will not necessarily end on a facet at the end of the process, because we're going to be in very high dimensions, so they are hard to find.
What do you do if, because, okay, in this case you have very few deterministic point vertices. What happens if, say, the first 10 times that you apply the algorithm, every time you want into a new vertex?
You will add 10 vertices to your active set.
But then are you still using, try to follow these parallel directions, or are you using the original one, the original method?
So you mean to move towards the best vertex?
Yeah.
I mean, I will use it up to the point where it's not worth it. This we can discuss with more formulas and stuff, which I haven't put in the
because in this case, we could have started doing it before or later, right? I mean, you could have follow the first algorithm, the original algorithm, for a while, and then you start doing this thing.
This is the important point. Yeah. In this very simple case, we were at the beginning finding the active set and then using it. But those are completely entangled interlaced in the actual implementation. So sometimes you see that you actually add a point, but sometimes you will move along pairwise lines and so on and so forth. It's not just that I want an active set and then I reduce it. It's really not the case. It's you keep building your active set while maintaining a clean representation of your iterate.
Okay, so then depending on which heuristic you use, then you will get a different algorithm, I guess, right? Or
yes.
Just ask it for me. How do you find the weight P? How do you
find the weight?
How do you know how to change the weight of the?
So
you say you move the weight
yes.
from the worst point.
So this is here.
Sorry, I'm asking the question again. So
in
how do you know how much weight to move?
So in this geometric example, and this is actually true in general, you actually want to go closest to your point. And this means that here you have a right angle, and this allows you to explicitly get the weight that you, yeah.
No, this I know, but when you have 3 points, you're saying, okay, I want to move from the worst to one of the previous. Like, is that also it's the deterministic? You know, you have a way to find out. Like in that whiteboard, now you wrote P0 minus P and P1 plus P. How do you find that P?
Exactly the same way.
Exactly
Exactly the
the same.
same way. Yeah, it's always the same way. I mean, you have a line, and you want to find the point on this line which is closest to your x star.
But you always have. But you can be a plane, no? Or
No, because it's a line. Here, it's really here it's a line. Very importantly, and also for the online audience, here it's a line, because you only have 2 points, the worst one and the best one.
Okay.
Yeah, good question. Yeah, I kind of voluntarily did not put any equation because I think for a talk is more confusing, but all the details are in the paper and I'm happy to discuss them while I'm here. Okay, now I can tell you a bit more what I mean by best vertex. And this is kind of standard. It was done in the previous works about this problem. By best vertex with respect to this m here, which is like the direction of the gradient in the previous picture, this amounts to finding the best deterministic strategy, which amounts to solving this problem, which is quadratic, as you can see. And okay, naively, you can enumerate all possibilities, but it soon becomes completely impossible. And then what was done previously, and that we are also doing, is to do an alternating maximization, also called seesaw in our quantum community. And this alternating maximization is doing the following. You fix, for example, A and optimize over B. and then you fix the resulting B and optimize over A, and so on and so forth. And because at each step it's linear, I mean, you have a closed form for the maximization that you're doing, and then it converges actually pretty quickly. So you start with a random point, you see where it gets, and you do that for a lot of random initial points. And yes, it's a heuristic. You have no guarantee of ending up in the good point, neither of being actually close to the good one. But this is really fast, and this is what we use. Later in the talk, I will tell you about a way to solve this exactly by connecting it with so-called quadratic and constrained binary optimization problems. More on that later. This was for this Frank-Wolfe algorithm, which was, again, performing some optimization over the local polytope of some distance function. We chose the distance because it suited our need, but the Frank-Wolfe method is general. And now, let's start with the case where we want actually to get an upper bound on the non-locality threshold. So to get an upper bound on the non-locality threshold, all you need to get in this geometrical picture is a Bell inequality that is separating your point from the polytope. So suppose that this is my local polytope, and this is my point. When I actually add noise to the shared state, this amounts in this picture of moving along this line. So this is when I have, let's say, a pure singlet state, if I'm working with the singlet state. And if the visibility goes slower and slower, I will move all the way down to 0. And what we are interested in, once we have fixed the scenario and hence this polytope, what we are interested in is this point here. Okay? Where do we actually enter the local polytope for this number of measurements? And I mean, a way to estimate it is just to say, okay, I will find with my algorithm the distance between the local polytope and my point. And once I've reached this orthogonal projection of my point on the polytope, I can just take this, take the hyperplane that is perpendicular to this direction. And this is a valid Bell inequality. It's going to separate my polytope from the point P. The problem, as you can see in this example, is that this hyperplane here has no chance, in general, to be a facet, because it's of a lower dimension than the full dimension of your problem. So what you actually kind of want to do is to move a bit on this line so that the orthogonal projection of your point gets onto a facet. Because if you're too far away from the polytope, somehow you could be in a bad case in which your orthogonal projection lives on a smaller dimensional subspace. And this is what this picture is trying to kind of convey in a sense. If I get really close, I mean sufficiently close to the actual threshold, then this vector at the end between the orthogonal projection and this point here on the line between 0 and P, this will actually be a valid Bell inequality. I mean a good one, which has chances to be a facet. And yes, this is exactly what we're doing, and I'm just putting this picture so that you see that in practice our point xt at the end of the algorithm is not going to be exactly the orthogonal projection. It's going to be a little bit away from that, so that the inequality you get out of it, like given by this line, would be slightly tilted, but slightly, but still way better than this one. Yes, and now a subtle and important point that I already mentioned before is that we have a heuristic during the algorithm, which means that at the end, we haven't computed any local bound. But we need a local bound if we actually want to have an upper bound on the non-locality threshold. And the way to get this local bound in the past, there were a few works about that, including one by Tomasz in 2017, Vertesi, who was devising a branch and bound algorithm to compute up to kind of 90 times 90 local bounds, which amounts to solving this optimization problem here that I mentioned before. But actually, you can rephrase that in terms of a QBO. A QBO is exactly this kind of problem, but for variables being 0 and 1, being binary. And it has gained some interest in the last few years, partly because some people claim that that quantum computers could be actually solving this efficiently. And yeah, I mean, it's an active field, and people have devoted some effort to give some nice classical solvers. And this is one of these solvers that we were using for our work. And when you
say that people believe that quantum computers can solve these problems, it's simply hard, no? This problem.
Yeah, they can get good approximations, I think.
Okay.
This is not the direction that I really looked at, but I know that part of the hype around QBO comes from the quantum computing community.
Okay.
That's all I can tell. But not solving, like getting.
But even polynomial approximation is simply harder, I think.
Yeah.
Or a polynomial in a number of, like n in this case.
Mm-hmm.
Yeah, so the hope is that the D-wave quantum annealer actually should be good at it, but of course it shouldn't be able to solve it. It's proven to be NP-hard to approximate up to approximation factor of 0.875. So it cannot get really good, but I mean, still any benefit is good, no, for NP-hard problems.
Yeah. Thanks, Mateus. So this was the upper bound part. So
how do you do it? How do you do it? I mean, what are the techniques that you use to solve this quadratic binary?
So this is the shadow part of the talk and of the paper as well. I discussed that with Mateus a bit this week. So unfortunately, the solver that we could have access to here is closed source. So someone published, Daniel from our institute published it like last year, and it's able to solve nice QBO instances, and we could solve one with 97 settings. Actually, okay, there is a chance that the latest release of Gurobi is able to outperform that, which we have missed. But in any case, this is the part that is a bit of a deception. I mean, I just provided him with a problem that he could solve, and I have to kind of, yeah.
But how do you know that the solution is sound? I mean, does it give you a proof also that
Yeah, I mean, the proof is the algorithm itself, exactly like with Thomas. With Thomas, you have a branch and bound, so you have to trust the algorithm. It's anyway in co-NP, so it means that the certificate itself is very big. I mean, there are examples of instances for which you have nice certificates, like for example, this first paper by Thomas beating the 1/√2, but they are really symmetric, and in general, the certificate is going to be the algorithm itself, which is exactly what happens in Thomas' paper, with branch and bound, and which is also the case for these solvers. So they are cutting strategies in an analytical way, but which is just the way the algorithm works. So they are using both those they are using those cutting plane techniques that I don't understand, but that are apparently pretty efficient. But yeah, this, unfortunately, we could only use it for our purposes, get a bit better on the upper bound, but yeah, it's not so nice. What is really nice is what's to come. I mean, in terms of insight that we got from the algorithm. So just to recap on this upper bound part, we have chosen the initial visibility in an empirical way so that it's close enough to the local polytope to get like a good Bell inequality. Because as I said, if you're too far away, the inequality is too tilted. And yeah, then we were able, in the bipartite case, to solve the local bound by means of QBO. when you are interested in getting a lower bound, this is an algorithmic method that was, I think initially, was it proposed by you, Flavien? Or there was a paper before by Paul, right? That was using this, this polyhedron method that I will tell you about right now. So now what we want is a decomposition of a point that is inside the polytope and that lives on this line here somewhere, namely here. The algorithm is not going to end up on this line, but it's going to end up close to this point here. And note that we have an explicit local model for this xt at the end. And this, regardless of the fact that we use the heuristic. Because, I mean, it's sufficient to have good atoms. You don't care that they were the best at some point in your algorithm. It's just that you have an explicit decomposition, it works. The problem is that xt is not V0p. You're not there yet. What you need to do, and this is what Flavien did a few years ago in 2017, is to actually go one step further and to say that you're actually close enough to exhibit a decomposition. So this is what you can do, and geometrically, it amounts to do that, which I'm going to try to explain you now a bit, quickly. The idea is that if you allow a little bit more noise here, like with this factor µ2, you actually have a decomposition, a local model, I mean, of this µ2 xt, which is here, because you have one for xt, so you can just shrink this model. And then you have also a model for this red vector that is here, because it is small. And this was an important lemma from Flavien's paper that we improved on to say that any correlation matrix tensor of 2 norms smaller than 1 is going to be in the local polytope. So that if you actually have here a vector that is of norm smaller than 1, and you choose it in the way that it actually has a norm 1, then you have a local decomposition of this point. So in total, you have a decomposition of this point here, because you have one from this out of the algorithm, and from this out of the fact that it has a small norm, so that it's in the interior of the local polytope. So this was to get a explicit local model in the finite scenario of our point P. I mean, with some noise. And now there's a last step that, again, we did not invent. It's just Flavien's method, is to go from this finite scenario to the infinite scenario. And the idea is to simulate all projective measurements by means of a finite number of them, and to use nice geometric tricks for that. When you have your set of measurements that is forming, let's say, a polyhedron in the Bloch sphere, then you can actually fit the Bloch sphere itself in the polyhedron. I mean, not for all of them, but if it's living in 3D, if it's not a square, let's say, in the equator, then you can fit all the Bloch sphere in this polyhedron. In this example, with the icosahedron, this is with up to a factor of almost 80%. And this means that if you take any observable in the Bloch sphere, by adding a bit of noise to it, you can actually decompose it as a convex combination of the points on your polytope, on these matrices here and there. And then, when you write down explicitly your probability and adding to the visibility an extra factor eta squared, then you can move the eta squared to the observables A and B, and then you can use the decompositions from before, so that in the end, for this point here, if you have managed to get a decomposition for this point here, then you have something for the infinite scenario. This is a nice algebraic step that I'm happy to take question on when there are such. And it allows to give a lower bound on the non-locality threshold, which involves eta, the shrinking factor, as we call it, of your polyhedron, nu2, which was this analyticity factor from the previous slide with this distance between the ending point of the algorithm and your v0p, like the point you're interested in, and the initial visibility v0. In order to do a bit better than Flavien's paper, we wanted to come up with nice polyhedra. A way to do that is to start, let's say, from this icosahedron and to triangulate all the faces, to add like a lot of different, you see, small triangles, and then to project everyone on the Bloch sphere. You end up with something that is kind of nice. It has a way better shrinking factor than the icosahedron before, and it has not so many measurements. I mean, compared to if you were trying to do something non-symmetric, let's say. And you can repeat this procedure, right? You can again triangulate all the different facets, and you keep going. And you end up with very nice symmetrical polyhedra that are having nice shrinking factors. Let me emphasize one thing about this. It would, of course, be an optimization problem to find the best distribution of the Bloch sphere, but it's a very, very hard one because it has the same flavor as this Thomson problem of placing electrons on the sphere. And this problem is known to be really hard. Like typically, with this Coulomb interaction between electrons on the sphere, the only analytical case known are 1, 2, 3, 4, 5, proof from 2010, I guess, and 6, because 6 is not the icosahedron, and 12, the icosahedron. All the others, we have good candidates, but no proof for that. So, I mean, a good heuristic for this is good enough. And with that, I've reached the end of the presentation of the method itself. And hopefully you have now understood all the different parts of this diagram. If you have questions about it, it's a good time before I move on to the results.
Yeah, okay. So I have, I think, 2 questions. The first one is, how do you choose the initial visibility? So you need an initial upper bound on the...
It's empirical. So on the examples, I have 2 answers for that. The first is on the examples we investigated, it was really empirical. So we had bounds existing, so we knew it was not higher than that, but it was still quite loose, right? And then we tried a few initial points, and at the end of the algorithm, you see whether you're on one side of if you're outside or inside the polytope, and then you can decide where to go for the next one. But this was pretty empirical. But in general, you could start from 1, which gives you a Bell inequality, that gives you a visibility, and then you start again your algorithm with this visibility. And you can keep going, and in a sense, it will kind of do the empirical job for you at the expense of probably calling the algorithm too many times.
Okay, and then if I understood correctly, you use Frank-Wolfe in the second part to get this point with which then you project to the line.
Yeah,
no?
exactly.
But where do you use it in the other part? Where I see another arrow to the left.
To the left?
Yeah.
Also to get the point that was getting closer to the projection, the orthogonal projection.
Okay, maybe I don't understand this because there was this cubo thing.
So if I just go back to this part here, without talking about cubo, you see here how to get to this point here, this orthogonal projection. This, for this simple example, is trivial, but in higher dimensions, it's a hard problem per se. What you need is a way to get to this orthogonal projection. And even though at the end we don't get exactly to it, because we are in really high dimensions, the better our algorithm is, the closer we're going to get to this orthogonal projection. And then the better the inequality is going to be. We will see that in the result, actually, at some point. If there are no more questions, let me go for the results, which are mostly going to be kind of a history of the three problems we considered, namely the Werner state, 2 qubits, the GH state, 3 qubit, and the W state, 3 qubits as well. So this is a small history of what happened on this problem. So the CHSH bound gave the first upper bound of 1 over root 2. And on the other side of the spectrum, there was Werner result with his model reproducing with a factor of 1/2. And then when Assine, Gisin, and Tonnerre made the connection with Grothendieck constant, this jumped immediately quite a lot, using some results from the math community. And it took actually quite a while for Tamás to come up with an example with a lot of measurements, really symmetrical, so that he could compute or at least estimate the local bound. A result that was then generalized by those people, and later on, Miguel and Steve and Tamás came up with this Frank-Wolfe-like algorithm to get a better bound with 42 measurements, and the limitation then was basically computing local bounds, and then Tamás came up with an algorithm to do that more efficiently, which is this 90 here, and on the other side, this algorithmic method to compute local models valid for all infinitely many measurements was done by Flavien in 2017. And yeah, this is in between that we have made progress here. Note that importantly, we actually don't need to go for so many measurements as was here. The reason for that is we can choose an initial visibility which is closer to the actual threshold. And most likely, I would, in this paper, you chose 689 over, 0.689 as an initial visibility, and I think one could have chosen 692, a bit higher, but of course it was limited by this zigzagging, so that the algorithm had to converge in a reasonable time, and this was fixing some, let's say, constraint on the initial visibility, right?
Yeah, we tried changing the visibility because I don't recall. We did this at least in the other paper for the upper bound, so I don't know if we did. We're also playing with that, right?
Yeah, we were playing with that.
Yeah, so we were doing this technique that you're using,
Mm-hmm.
just getting closer to get the best faster. Yeah.
But you mean for the upper bound or for the lower bound?
For both.
Okay.
Yeah. I guess one other possible reason is the tessellation that you chose, right? I mean, to approximate the ball, right?
Actually, no. And this I can show you in this new table for the GHS state. And for this GHS state here, we're using exactly the same measurements as you were using. But because the algorithm has a better conversion rate, we end up actually in this case with a facet. So we get this facet here, and then this is like for these measurements, which are thought to be like the best ones for the GHS state, with a better bound. And the improvement really just comes from the better algorithm. Yeah, I want to emphasize here, I will not go through all the details of the history, but there is a very nice gap here that we fill, and yeah, we are far above the separability threshold, which is pretty nice. What's also nice is that here you see the upper bound is 4916, and if I go for the W state here, the lower bound is 4938, which means that the non-locality of the W state is less robust to noise than the one of the GH state in the tripartite case. There are results for more parties, but in the tripartite case, this is the first proof that this is indeed the case. And yeah, we can go a bit more into the details if we're interested, but now I'd like to conclude. So to summarize, we used improvements on the Frank-Wolfe algorithms from the optimization community, but not only, also improving on the analyticity factor and also on the polyhedra. I didn't mention the fact that we were getting all the shrinking factors analytically, which is important to get an analytical bound at the end. And all this procedure to construct local models and Bell inequalities for the Werner states, 2-qubit, but also for tripartite GH state and W states. Let me stress that our implementation is available online. We made a Julia package so that people can play with it. For the moment, it's limited to 2 outcomes and the same number of inputs per parties, but it's already completely general in the sense of multipartite. And yeah, the next steps are to go for more outputs, either for POVM in the qubit case or also projective measurements in the qubit case. And potentially to try to apply this nice first order method for other optimization problems in high dimensions. And potentially for SDP, maybe it could be an option. And with that, I'd like to thank you for your attention.
What is known about the Frank-Wolfe algorithm, like theoretically? What is the worst case scenario when you consider this active set that you were speaking about?
The convergence rate is also linear. I think theoretically it doesn't change much. I mean, it's just like a nice technique that works well. But yeah, my collaborators were mostly responsible at this part, so
I'm curious about the more outputs case, because I mean we know that there is no Grothendieck constant if you have more than 2 outputs. Then what do you mean?
So what I mean in this qubit POVM sentence, for example, it would be to do the very same to get lower bounds that are valid for all POVMs. And then, of course, it's not related to Grothendieck constant, but it's related to the non-locality threshold under all POVMs. And this is not of interest for mathematicians, but of interest for quantum physicists, given the fact that the gap at the moment is completely empty between 0.45 and our upper bound. So it's really loose, and hopefully we can tackle that. And the second example that I mentioned here is it's not Grothendieck constant, but it would be the non-locality threshold of, let's say, the isotropic state in dimension 3 under projective measurements. And then, again, you have a similar problem, let's say, for which I don't know of any, of any good bounds, let's say. Lower bounds, I mean.
Yeah, okay, of course. Yeah, no, that makes perfect sense. No, I was thinking about, if you allow for arbitrarily many outputs, then yeah, there is no locality threshold. You can always go arbitrarily close to 0. But yeah, but then it's physically, of course, it makes sense to consider this scenario.
Good.
So, do you know more about this Frank-Wolfe method, or maybe we can discuss it later?
We can discuss that. Yes.
Okay.
Yeah. What I can tell you, a nice thing in the name is lazy. They call it lazy blended pairwise conditional gradients. So conditional gradients is Frank-Wolfe in the sense that you're optimizing your gradient, but conditioned to the fact that you want to stay in the active set. In the feasible set, which is why you end up being on a vertex because you have a convex function. And so this is conditional gradients. Then blended pairwise is this line stuff that I explained at the beginning. And lazy means that we are not computing this best vertex, this LMO, linear minimization oracle, at each step. This is this estimation that I mentioned. And all of them were kind of separate ideas that were merged, let's say, into an algorithm that was implemented, not by me, but by a collaborator there. And he released, I think, 2 years ago or 1.5 years ago, a package that we are building on to offer our implementation.
What other uses apart from quantum information does this have?
Given the fact that it's for any function, and not only like the distance function. It's used, as far as I can understand, in machine learning as well, because they have big problems, big optimization problems, for which at some point second-order methods or fail somehow. So they go for first-order methods, and they're happy with it somehow. What's really important is that for some applications, not ours, but if you do a normal gradient descent, you go outside of the feasible region, and then you have to project back. And this can be really, really expensive in high dimensions, especially in machine learning, which is why people started looking at this Frank-Wolfe a bit more into details. Because the method, the paper by Frank and Wolfe, who were actually together, I mean, it's Marguerite Frank, and I don't remember his name, but it's from '56. So it's really a long time ago, and it's only recently that people reconsidered it because it was giving some speed up in high-dimensional applications.
You're still in an oracle that has linear optimizations, right? So it's
depends. For some, I mean, you call it an oracle, but for some applications, it's actually really easy to do. If you, for example, if you're optimizing over the spectraplex, over the set of positive matrices of trace one. If you're optimizing over that, then the LMO is fully exact. It's only computing the exactly. And then, I mean, you can do with that very efficient methods when you have like huge matrices that don't need to project on the set on this set of positive matrices of trace one. So yeah, this is one of the other applications. At least in the package, there is one LMO that is doing that. Not my package, Mathieu's one. So I guess people are using it.
Okay. Any more questions? Stand the speaker.